The factory method design pattern is a fundamental creational design pattern that focuses on defining an interface or abstract method for creating objects, while allowing subclasses or derived classes to decide which specific class to instantiate. Instead of directly creating objects using constructors or the new keyword, the pattern delegates this responsibility to a factory method. This approach promotes loose coupling by separating object creation from its usage, ensuring that the client code depends only on abstractions rather than concrete implementations. In modern software development, especially in .NET applications, this pattern plays a crucial role in building scalable and maintainable systems. At its core, the factory method pattern encapsulates the instantiation logic within a dedicated method, making it easier to manage and modify without affecting the rest of the application. This becomes particularly useful when the system needs to support multiple types of objects that share a common interface or base class. Instead of scattering object creation logic throughout the codebase, developers centralize it in one place, improving readability and reducing redundancy. Another important aspect of the factory method is its alignment with solid principles, especially the open/closed principle. This principle states that software entities should be open for extension but closed for modification. With the factory method, new object types can be introduced by adding new classes and updating the factory logic without altering the existing client code. This makes the system more robust and adaptable to change. In .NET development, the factory method pattern is widely used in frameworks, libraries, and enterprise-level applications where flexibility and extensibility are essential. For example, dependency injection containers, logging frameworks, and service providers often rely on factory methods to create instances dynamically at runtime. By abstracting object creation, developers can easily switch implementations, test components independently, and maintain cleaner architecture. Overall, the factory method design pattern provides a structured and scalable way to handle object creation, making it an essential tool for developers working on complex and evolving applications. The factory method pattern is essentially a design approach that shifts the responsibility of object creation from the client code to a dedicated method, often referred to as the factory method. Instead of directly instantiating objects using specific class names, the client interacts with a method that returns an object based on certain conditions or inputs. This method determines which class to instantiate and returns it as an interface or abstract type, ensuring that the client remains unaware of the underlying implementation details. In traditional programming, developers often write code like new product A or new product B, which tightly couples the code to specific classes. This makes the system rigid and difficult to modify when new types are introduced. The factory method pattern eliminates this issue by introducing a level of abstraction. The client code only knows about the common interface, for example, iProduct, and relies on the factory method to provide the correct implementation. This pattern is particularly useful in scenarios where the type of object to be created depends on runtime conditions, user input, or configuration settings. For instance, consider a payment processing system where users can choose between credit card, UPI, or net banking. Instead of writing multiple conditional statements throughout the application, a factory method can handle the decision-making process and return the appropriate payment object. Another key aspect of the factory method pattern is its ability to improve code organization. By centralizing object creation logic, developers can avoid duplication and ensure consistency across the application. It also makes the code easier to read and understand, as the creation logic is clearly separated from business logic. Furthermore, the pattern enhances testability. Since the client code depends on abstractions rather than concrete implementations, it becomes easier to mock or replace objects during unit testing. This leads to more reliable and maintainable code. In summary, the factory method pattern is about creating objects in a controlled and flexible way, using a method that determines the appropriate class to instantiate. It promotes abstraction, reduces coupling, and improves the overall design of the system. The factory method pattern is best suited for scenarios where the exact type of object to be created is not known at compile time and must be determined dynamically at runtime. It is particularly useful in systems that need to support multiple variations of objects that share a common interface or base class. In such cases, directly instantiating objects can lead to tightly coupled code and make the system difficult to extend or maintain. One common use case for the factory method pattern is in applications that handle multiple types of services or operations. For example, in a payment gateway system, users may choose different payment methods such as credit card, UPI, net banking, or digital wallets. Instead of embedding complex conditional logic throughout the code, a factory method can be used to create the appropriate payment object based on user input. This simplifies the code and makes it easier to add new payment methods in the future. Another area where this pattern is widely used is in notification systems. Applications often need to send notifications through different channels such as email, SMS, or push notifications. By using a factory method, the system can dynamically create the appropriate notification service without modifying existing code. In .NET development, the factory method pattern is commonly found in frameworks and libraries that require flexible object creation. For instance, logging frameworks may use factory methods to create different types of loggers, file, database, console, while document generation systems may use it to produce PDFs, Excel files, or Word documents. The pattern is also useful in scenarios where object creation involves complex logic or multiple steps. Instead of exposing this complexity to the client, the factory method encapsulates it, providing a clean and simple interface for object creation. Additionally, the factory method is beneficial in large-scale enterprise applications where maintainability and scalability are critical. As the system grows, new object types can be added without disrupting existing functionality. In essence, the factory method pattern should be used wherever there is a need for flexibility in object creation, especially when dealing with multiple implementations, runtime decisions, or evolving requirements. The primary reason for using the factory method pattern is to reduce tight coupling between classes and improve the flexibility and maintainability of the code. In traditional approaches, when objects are created directly using constructors, the code becomes tightly bound to specific implementations. This makes it difficult to modify or extend the system, as any change in object creation requires updates in multiple places. The factory method pattern addresses this problem by introducing an abstraction layer between the client and the object creation process. Instead of depending on concrete classes, the client interacts with interfaces or abstract classes. The factory method takes care of deciding which implementation to instantiate, allowing the client to remain unaware of the details. Another important reason for using this pattern is to support the open/closed principle. As software systems evolve, new requirements often emerge, such as supporting additional object types. With the factory method, developers can introduce new classes without modifying existing code, making the system more adaptable and less prone to errors. The pattern also improves code organization by centralizing object creation logic. This eliminates duplication and ensures consistency across the application. When changes are needed, developers can update the factory method instead of searching for object creation code scattered throughout the system. Moreover, the factory method enhances testability. Since the client depends on abstractions, it becomes easier to replace real objects with mock implementations during testing. This leads to better unit testing practices and more reliable software. Another advantage is improved readability and maintainability. By separating object creation from business logic, the code becomes cleaner and easier to understand. Developers can focus on the functionality of the application without worrying about how objects are instantiated. In summary, the factory method pattern is used to create flexible, scalable, and maintainable systems. It reduces coupling, supports extensibility, and simplifies code management, making it a valuable design pattern in modern software development. Without the factory method pattern, object creation is typically done directly within the client code using constructors. For example, a developer might write var payment equals new credit card payment, or use multiple conditional statements to decide which object to create. This approach leads to tightly coupled code, where the client is directly dependent on specific classes. As a result, any change in the object creation logic requires modifications in multiple parts of the application, increasing the risk of errors and making the system harder to maintain. In such scenarios, the code becomes cluttered with if-else or switch statements, especially when dealing with multiple object types. This not only reduces readability but also violates the open/closed principle, as adding new types requires modifying existing code. With the factory method pattern, the object creation logic is centralized in a factory class or method. Instead of directly instantiating objects, the client calls a method like paymentFactory.createPayment (UPI), which returns the appropriate object. This approach decouples the client from concrete implementations and allows the system to work with abstractions. The benefits of using the factory method become more evident as the system grows. When a new payment method is introduced, developers only need to update the factory method without touching the client code. This makes the system more scalable and easier to maintain. Additionally, the factory method improves code clarity by separating concerns. The client focuses on using the object, while the factory handles its creation. This leads to cleaner and more organized code. In conclusion, the difference between using and not using the factory method lies in flexibility and maintainability. While direct instantiation may seem simpler initially, it becomes problematic as the system evolves. The factory method provides a structured and scalable solution for object creation. The factory method pattern is implemented by defining a common interface or abstract class, creating multiple concrete implementations of that interface, and then introducing a factory class or method responsible for creating and returning the appropriate object. This structure ensures that the client interacts only with abstractions, while the factory handles the details of object instantiation. The first step is to define an interface or base class that represents the common behavior of all objects. For example, in a payment system, an interface like iPayment can be created with a method such as pay. This interface serves as a contract that all concrete classes must follow. Next, multiple concrete classes are implemented, each representing a specific type of object. For instance, credit card payment and UPI payment would implement the iPayment interface and provide their own implementations of the pay method. The final step is to create a factory class with a method that takes input parameters and returns an object of the appropriate type. This method uses conditional logic or other mechanisms to determine which class to instantiate. The client code simply calls this factory method and receives an object without knowing its exact type. This approach ensures that object creation is centralized and controlled, making the system easier to manage and extend. It also allows developers to modify or enhance the creation logic without affecting the rest of the application. In practice, the factory method can be further enhanced using dependency injection, configuration files, or reflection to make the system even more flexible. This is especially useful in large-scale .NET applications where object creation may depend on external factors. Overall, the implementation of the factory method pattern involves abstraction, encapsulation, and delegation, resulting in a clean and scalable design. In a real-world e-commerce application, the factory method pattern plays a crucial role in handling multiple payment options efficiently. When a user proceeds to checkout, they are typically presented with various payment methods such as credit card, UPI, net banking, or digital wallets. Each of these methods has its own processing logic, validation rules, and integration requirements. Without the factory method pattern, the application would need to include multiple conditional statements throughout the code to determine which payment class to instantiate. This would lead to duplication, increased complexity, and difficulty in maintaining the system as new payment methods are introduced. By using the factory method pattern, the application can centralize the object creation logic in a single factory class. When the user selects a payment method, the system passes this information to the factory method, which returns the appropriate payment object. The rest of the application interacts with this object through a common interface, ensuring consistency and simplicity. For example, if a new payment method like a digital wallet is added, developers only need to create a new class and update the factory method. The existing code remains unchanged, demonstrating the power of the open/closed principle. This approach not only improves scalability but also enhances code readability and maintainability. It allows developers to focus on business logic rather than worrying about object creation. In enterprise-level applications, this pattern is often combined with dependency injection frameworks to further improve flexibility and testability. The factory method pattern offers several advantages that make it a popular choice in software development. One of the most significant benefits is loose coupling, as the client code depends on abstractions rather than concrete classes. This makes the system more flexible and easier to modify. Another advantage is support for the open/closed principle, allowing new object types to be added without changing existing code. This enhances scalability and reduces the risk of introducing bugs during modifications. The pattern also centralizes object creation logic, improving code organization and reducing duplication. This leads to cleaner and more maintainable code. However, the factory method pattern also has some drawbacks. One of the main disadvantages is increased complexity, as it requires additional classes and interfaces. For simple applications, this may be unnecessary and can make the code harder to understand. Another drawback is the potential for over-engineering. If the system does not require dynamic object creation or multiple implementations, using this pattern may add unnecessary overhead. Despite these disadvantages, the benefits of the factory method pattern often outweigh its drawbacks, especially in large and complex applications. The factory method design pattern is a powerful and flexible approach to object creation that delegates the responsibility of instantiation to a dedicated method. By introducing abstraction and encapsulation, it reduces tight coupling between classes and promotes better software design. The pattern aligns with key principles such as the open/closed principle, making it easier to extend applications without modifying existing code. In .NET development, the factory method is widely used in scenarios where object creation depends on runtime conditions, such as payment systems, notification services, and logging frameworks. It helps developers build scalable, maintainable, and testable applications. Although the pattern introduces some complexity, its advantages in terms of flexibility, code organization, and extensibility make it an essential tool for modern software development.